Okay, the next chapter is chapter 7, nonlinear optimization models. So what is nonlinear optimization? Well, okay, the objective and or the constraints are nonlinear functions of the decision variable. So for linear programming, the objective function and all the constraints needed to be linear functions of decision variables. Now, even if any one of these, either the objective function or any one of the constraints is a nonlinear function of the decision variables, then linear programming model cannot be applied. So you cannot select LP simplex LP in solver. So you have to select GRG nonlinear in solver. So when you do that, when you select GRG nonlinear, then the solver solution you find may not be optimal. Okay, if it is a linear simplex LP, if you select simplex LP, then you're guaranteed to get the optimum solution. If you have to rely on GRG nonlinear because of nonlinearity in the objective function or the decision variables, then you have this problem. The solution may or may not be optimum. So how do we deal with that? So we will talk about that in just a second. But before that, let's see where the nonlinearities come from. So the effect of some input on the output is nonlinear. For example, if you have pricing models, the price is the decision variable. You want to set a particular price based on other factors, say quantity that you can sell is related to price. So if you increase price, your quantity of sales will go down, and because of that, the revenue may or may not go up. And this relationship often is nonlinear. Another example of nonlinearity is goodness of fit. So when you have a set of data and then you want to fit a curve or a straight line through the points, like in regression analysis, then what you get is minimization of the sum of squared differences between the model that you want to fit and the points. So that squared difference then is a nonlinear function. And also in financial models, where you have to achieve high levels of return at low levels of risk, and often risk is modeled in terms of variance or standard deviation. And when you use variance or standard deviation to measure risk, then that is nonlinear. So there are many examples like this, and these are some that introduce nonlinearity into our problems. When you have nonlinear functions, your objective function can look like this. Okay, it goes up, then comes down, goes up and comes down. So that's an example of nonlinear function, and that gives rise to what are called local and global optimum. So if you start your model in a place like this, if your initial solution is like this and you're trying to maximize, so your GRG nonlinear will try to find the larger of these values, and it will keep going up and up and up. Once it reaches the peak here, then it goes down. So then it will say, okay, A is the optimum solution. But suppose if you start your solution from a point right here, if GRG nonlinear model starts the solution from here, then it's going to go up this way, because going this way will be going down for a maximization problem. So you go up and up and up, and you hit the peak, and then you stop there, and you say, okay, I have reached the maximum, because if I go any further, I'm going to go down, and that's not maximum. So GRG nonlinear will stop at this point. Okay. But when you have a larger picture, then you know that C is not global optimum. It is a maximum value right in that neighborhood. But the global maximum is here. But when you run GRG nonlinear, you don't know whether you have reached a global optimum or a local optimum. So when you're here, you don't know whether there is another point which is higher or all other points are lower than C. You don't know that. So how do you make sure that solver will find A? And that's what the problem is. So whether you have a local optimum or a global optimum. So we'll talk more about global and local optimum in just a few minutes. Let's see under what conditions you're guaranteed to get global optimum. So when you have convex functions and concave functions, then you will get global optimum. You are guaranteed to get GRG global. GRG methodology will give you the global optimum. A function of one variable is convex in a region if the slope, that is the rate of change, is always decreasing. So in other words, an easier way of looking at this is if you connect 2 points, any 2 points on the curve, and if the connecting 2 points on the curve the curve is always below. So the curve that this point is always below the line. So this is one example. Here is another example. In these two examples, if you connect any 2 points, the curve will always be below the line. Okay. And if you have a function like that, and that is called a convex function. So convex function will give you the minimum value. If it is of this kind, then you will have a minimum. If it is of this kind, you will not have a minimum because this line keeps going down and down and down without ever reaching a valley point. And similarly, concave is the other way around. So when you connect 2 points, if the curve is always above the line, okay, then that would be a concave function. And if a concave function is like this, you'll get a maximum value, optimum, that would be the global maximum. But if it is like this, where it is always increasing, but the rate of increase declines, and it just goes on and like this, then you will not have a unique optimum or global maximum. This will be the case where you have unbounded solution. So some other properties, if you sum concave functions, the resulting function is concave or convex. If you sum convex functions, the resulting function is convex. And if you multiply functions of the same type with a positive constant, then the resulting function is of the same type. Convex means convex, concave means concave. Also, if you multiply a convex or a concave function with a negative constant, then the opposite will happen. Convex will become concave, concave will become convex. So GRG linear, nonlinear solution methodology will give you global optimum if you have concave functions. If it is convex function, then you will have minimum. So if previous conditions are not true, suppose if you do not have concave or convex, then what do you do? So in that case, all you have to do is to try different starting points. So when you have a situation like this where it is not concave or convex, then you have to try different initial solution and select and then gather all the final solutions you got from different initial starting points and then select the one that is best. So that way you can be sure that you got the global maximum or a global minimum. There is no 100% guarantee, but you can do that. Now, Solver offers you a way of trying many different possible starting points. Okay, when we go to GRG nonlinear, we can use the multi-start option so that Solver itself will try many different starting points. So our confidence that we have reached the global optimum is increased. And for that, you have to go to options first and then click GRG nonlinear and make sure that multi-start is checked. And if you check this require bounds on the variables, then you have to provide a lower bound and upper bound constraint in Solver. So if you don't check that, then you don't need to do that. So if you put a check, then if you know that a variable cannot go below a lower limit and it cannot go above a certain upper limit, then you can include that. And so the Solver will do the multi-start in a more efficient way. This is very useful if you have a very large problem. Then you can restrict the number of possibilities for multi-start.